In this lecture, we are going to study how hypervisors are built using the full virtualization technique. So this lecture immediately follows the lecture on hardware assisted virtualization, where we've seen how hypervisors are built when the underlying CPU has virtualization support. In this lecture, we are going to see how virtualization happens when the underlying CPU does not have virtualization support. So full virtualization came up because the initial x86 hardware lacked virtualization support. We've seen a few lectures ago that there are certain instructions that do not run well when the guest OS is virtualized and is run in a lower privilege level, that they make it difficult to build a trap and emulate kind of hypervisor. But there have existed systems, the first one being the VMware Workstation, which actually efficiently solved this problem of building a trap and emulate hypervisor for x86, even when the underlying instruction set had these issues of being difficult to virtualize. So we are going to see in today's lecture, we are going to see how this is done when the underlying instruction set does not easily support virtualization. How do you go ahead and build a trap and emulate hypervisor? So this VMware Workstation is an example of a type 2 hypervisor, and that is roughly the model. A simplified version of that is what we are going to study in this lecture. So the key idea of how you do virtualization when the underlying instruction set is not easily virtualizable is basically binary translation. You take the OS binary and whatever are the problematic instructions that do not run well at low privilege levels, you will translate those in order to trap to the VMM or to behave correctly at low privilege levels so that the issues with the underlying instructions are sorted. And this binary translation is done on a dynamic basis, on a need basis. You don't have to translate the entire OS image. You translate only the parts of code you wish to execute. And note that the key thing is this is binary translation. This is not rewriting source code, which is the idea of para-virtualization. This is easier than rewriting OS source code. This is only translating the OS binary so that the problematic instructions which are hard to virtualize do not pose a problem anymore, and you can easily build a trap and emulate hypervisor. So of course, if you have hardware support, if your hardware supports VMX mode, like we've seen in the previous lecture, you can do hardware assisted virtualization. That is better because binary translation incurs some overhead as compared to natively running the OS in hardware assisted virtualization mode. But if the hardware support is not available, that is when this idea was developed. In such cases, full virtualization is beneficial. So we are going to see a simple architecture of a VMM using the idea of full virtualization. The VMware Workstation paper is the basis, but we have simplified some of the details here. So this kind of VMM also typically has two components, a user space component and a kernel driver component. You will find many similarities with the KVM QEMU model. So the user space component memory maps some memory to serve as the guest VM's physical memory. And then it invokes an IOCTL command, somehow communicates with the kernel driver and says, okay, now go ahead, run this guest VM for me. And this is in ring 3, and of course the kernel driver is part of the host OS that is running in ring 0. Now, just like how KVM QEMU does a switch to VMX mode, this hypervisor also performs a switch to the VMM context, and this is called a world switch. Note that there is no hardware support here. There is no separate mode in the hardware, but this is a purely software-based world switch to the VMM context. And once you're running the guest VM, what are all the various components? You have the VMM that runs in the highest privilege level of ring 0. And whenever the guest OS has to do a privileged operation, it traps here. And you have the guest OS itself that has been translated to run in ring 1 in a less privileged level than ring 0. And of course, you have the guest user applications that are running in ring 3 as usual. And anytime the guest OS needs to perform a privileged operation, it traps to the VMM. The VMM can handle some privileged operations on its own, since it's running in ring 0. But some things that require the host OS support, in such cases, the VMM will exit back, will switch back into the host OS context. For example, if some IO needs to be handled, the VMM will switch back into the host OS context, and the host OS might return back into the user space process. And the user space process can then perform the IO using existing system calls. Right? Instead of the VMM here implementing all the system call logic, it simply goes back to the host OS, the VMM process, which will do the IO on behalf of the guest. Right? And of course, once the VMM's job is done, it can once again switch back to run the guest OS in the VMM context. So what do these terms mean? The host context and VMM context, they just define a context. We've seen the CPU context is the values of various CPU registers, which point to the page tables, IDTs, and so on, right? So a context defines a certain execution environment, defines the address space. For example, in the host OS context, this is how the address space looks like. The host user processes occupy low virtual addresses, the host OS occupies high virtual addresses, and the page tables map these addresses to corresponding locations in physical memory. The IDT points to some interrupt handlers in the host OS. The CPU registers have values pointing to the address space of the host, and so on. Right? So this is the host OS context. This is how applications look like when they're running on the host OS. And of course, the host OS also has the VMM kernel driver as part of it. And the VMM user process runs in the host user space. Now, when the world switch happens, how do things look like in the VMM context? So the guest user processes, of course, run at low virtual addresses as usual. The guest OS runs in ring 1 in high virtual addresses. And the top 4 MB of the address space of all guest processes is occupied by the VMM code. Some special VMM code inserts itself into the top 4 MB of every address space. What does that mean? The CR3 is pointing to a page table, and that page table, the top 4 MB of the addresses in that page table point to VMM code. So this is the context in which the guest VM is running. This is the address space that guest user processes see. The IDT points to certain entries set up here. The page table points to these addresses, and so on, right? So this is how processes look like when they are running on the host OS, and this is how processes look like when they are running in the VMM context. Now, when you have to switch from this context to this context, what do you have to do? You have to store all the values of the CPU registers, the page tables, CR3, all of that you have to store and restore these values. And now the CPU will run in the host OS context. It will execute the host OS code. Then when you switch back, it will execute the guest code in the VMM context, right? So you need to switch back between these two contexts to switch execution between the host and the guest. Now, where is all this context stored? So there is a special page of memory. It is also referred to as the cross page, in which this code and data needed for this context switch, needed for this world switch, is stored. And this page has to be accessible both from the host as well as the guest. Therefore, this page is mapped into the VMM kernel driver as well as the VMM code in the VMM context. It is mapped into both these page tables. That is, certain addresses in the host address space as well as some addresses in the guest address space point to the same memory page. So that when the VMM kernel driver wants to switch here, it will save context, restore context from the same memory location. When the guest wants to switch back, it will save and restore context from the same memory location. That is, there is this special memory page that is mapped into both address spaces of the host as well as the guest in order to be able to do this world switch, right? So at this point, let us pause and understand the differences between QEMU KVM design that had hardware support and this particular design that does not have hardware support. So the first difference, where is the context saved? When you have to move from host to guest, guest back to host, you have to save and restore CPU context, values of page tables, IDTs, and EIPs, and stack pointers. All of these have to be saved and restored. So where is all this context saved? We've just seen that in this full virtualization based design, you need a certain special memory page that is mapped into both address spaces like this, right? In both page tables point to the same memory page, so that in both host and guest context, you can access this cross page and you can save and restore context there. But you have no such thing in the KVM QEMU design, because there was a common memory area called VMCS that was directly accessible by the CPU. The CPU knew where this VMCS was. It knew where to save context, where to restore context. There were special CPU instructions to launch VMs, to exit from VMs, which did this context saving. And therefore, this common memory area was automatically accessible to the CPU. You didn't have to specially insert any cross page into the guest OS or the host OS, right? The CPU took care of it. This is what we mean by hardware support. The CPU knows how to switch between two contexts, whereas in the full virtualization design, where there is no CPU support, the CPU does not know how to switch, so the software will manually store and restore context. So the second design, the second difference with respect to KVM QEMU is that of the privilege level of the guest operating system. In this full virtualization based design we are studying in this lecture, where hardware support is not available, the guest runs at a lower privilege level in ring 1, and any privileged operation, it has to trap to the VMM that is running in ring 0, right? And instructions that don't run correctly in ring 1, examples of which we've seen before, all those instructions are translated so that they trap to the VMM. The guest is modified so that it runs correctly in ring 1 at a lower privilege level and traps to the VMM. Whereas in the case of KVM, you didn't need any such translation, because the guest OS automatically ran in ring 0, but this was a special VMX ring 0, and we could configure what instructions should trigger and exit back to KVM. We could configure. We didn't have to rewrite the instructions to trap, but the hardware took care of this exiting back to KVM. The hardware took care of certain instructions cannot run in VMX mode. I will have to exit back to KVM. This was managed by the hardware. Whereas here, because there is no hardware support, we have to explicitly rewrite instructions so that they suitably trap to the VMM. So the next question is, how is this trap to the VMM itself happening? In this current design that we've seen in full virtualization without hardware support, the VMM is also located in the guest context. It is part of the guest address space. It is part of the address space of every process running in the guest, and it is located at the top 4 MB. Therefore, in order to trap to the VMM, the guest OS simply jumps to this top 4 MB of the address space and executes the VMM code, right? So trapping to the VMM happens in this fashion. And of course, if this VMM cannot handle the trap, it can also exit back to the host context, right? So this is how trapping to VMM happens. Whereas in KVM, there was no VMM in the guest context. The guest OS was running without any VMM running in the same context. There was no VMM code when the guest OS was running. And the trap happened via VM exit. Whenever the guest OS wanted KVM support, it exits back into the non-VMX root mode and runs KVM, right? Whereas here, you don't have to do a world switch. You can first trap to the VMM code which is present in the guest address space itself, and trap and exit back to the host. Do a world switch to the host only if required, right? So there are significant differences. How the context is saved, how this common memory where context is saved is managed, what is the privilege level of the guest, how this trapping happens, is the VMM located in the address space of the guest or not. So there are significant differences from KVM QEMU, because here with KVM you had hardware support, but in today's lecture, the design we are seeing, there is no hardware support. But modulo these differences, the key idea is the same, where you have a user space process, a kernel module, you have the world switch to the guest context, and so on. At a high level, the idea looks the same. but there are important differences. So now let us understand this concept of binary translation in more detail. So in the guest context, in the VMM context, the guest user process is run in ring 3. The guest OS is located at certain virtual addresses, but the guest OS's code is translated and placed into a translation cache inside the VMM address space, because this is untranslated guest OS code, right? It might have some sensitive, unprivileged instructions which are not safe to run in ring 1. So all such instructions are suitably translated, placed into a translation cache inside the VMM, and this is where the guest OS executes from. We never run the guest OS binary directly. We always run the translated guest OS code in ring 1. And of course, whenever it has to trap, it jumps to the VMM code in ring 0. Right? And this guest OS binary is translated instruction by instruction and stored in the translation cache. Now this translation cache is part of the VMM memory. And of course, this translation for the most part is easy. Most code stays the same, right? Most of the code that is loading values into registers, doing computation, all of that, you don't have to translate. The guest OS code as is copied into the translation cache. But you will still have to do some modifications. For example, we have seen that there are some sensitive but unprivileged instructions which run in a buggy fashion in ring 1. Those instructions you will have to modify so that they trap to the VMM and they can be executed correctly in ring 0. Right? So some such small changes have to be made to guest OS code, and those changes are made, and the translated guest OS code resides in the translation cache, and from here the guest OS is run. Right? And privileged OS code, wherever you need privileged operations in the guest OS code, all of those cannot run in ring 1, so they all trap to the VMM. Examples are any kind of IO instructions, instructions that modify CPU state like the IDT register, the CR3 which points to the page table. Any such operation is disallowed in ring 1. So all such instructions trap to the ring 0 and the VMM emulates them. So this is the classic trap and emulate architecture. Right? For example, if the guest OS says set page table, here is my page table, set CR3 to this value, that is a privileged instruction that traps to the VMM. Then the VMM maintains its own copies of data structures like page tables, IDT. It can use the guest values, it can modify them slightly, and VMM will go ahead and set the CR3 or IDT to its own copies. Right? So all privileged operations are done by the VMM. If the VMM does not want to use the guest's data structures like IDTs or page table, it will maintain its own copies and it will point the CR3 or IDT to its own copies. Right? So the essence is that the guest runs, most operations don't require privilege. All those operations run in ring 1 as normal, most instructions. Some instructions that require higher privilege level trap to VMM, and the VMM will emulate that instruction on behalf of the guest OS. The classic example is setting the IDT register or the CR3 which points to the page table. Whenever the guest tries to execute it, it traps to the VMM and the VMM will set to its own copies of these data structures. So these copies are called shadow copies because they shadow whatever the guest OS has. VMM will use a similar data structure and set CR3 or IDT register to point to its own data structures. So another thing to notice that this translation is dynamic. You don't translate the entire guest OS binary. Instead, the VM translator logic, the VMM's code, which does this translation, this runs in ring 0, of course, right? The translator runs in ring 0. The translated guest code runs in ring 1. So what this translator will do, this VMM code, it goes to the guest, fetches one block at a time, one basic block at a time, translates it to what is called a compiled code fragment or a CCF, and then jumps to ring 1 to run this guest OS code. So what is a basic block? A basic block is a sequence of instructions until some jump, return, some such control flow change happens. right? So what does the VMM do? It will take the guest OS code. It will see a sequence of instructions until there is a jump. It will take this block, translate it, produce what is called the CCF. So this CCF is stored in this translation cache, which is part of the VMM's data structures, right? So this basic block is translated, the CCF is produced. Now all of this translation is done by the VMM. And now you move to ring 1, execute the guest OS code, right? Once the CCF is created, run the guest OS code. Now at the end of the CCF, what do? Now it says jump to some location, but that location's code you've not yet translated. So then you go back, the VMM translator logic kicks in, it goes to the guest OS, fetches the next basic block, translates it, and now jumps to ring 1, executes the guest OS code. So this goes on multiple times, right? As long as the guest OS is running, you translate it block by block, put it into the translation cache, and then move to ring 1 and run the guest OS code. Note that after a time, what happens if the CCF says jump to some other address, that next block would also have been translated sometime in the past. So if the next translated block is already available in the translation cache, you can simply jump to it and run it. You don't have to go back and translate every time. So after running for certain period of time, most of the common pieces of guest OS code are already translated. So then you can directly keep jumping between them in the translation cache. So this is an optimization called chaining. You don't have to go back, translate every time. You can just use existing translated code that is there in the translation cache. So to summarize, this is binary translation. Basic block by basic block is translated, put in the translation cache, and then the VMM moves to ring 1, executes the guest OS code in ring 1 on the CPU. So now there is a certain use of segmentation. So we have studied in previous lectures that segmentation is not widely used for any kind of protection in modern operating systems, but this particular VMM design requires extensive use of segmentation, which we'll see just in a little bit, right? Normally, what do? In a regular operating system, there is, in the address space, you have the host user space, and then you have the kernel part of the address space in the host. So for these things, how do you protect the kernel from the user processes? Mostly paging is used for protection. That is, page tables have a certain bit that is set, which indicates some pages are user pages, some pages are kernel pages. So when the CPU is running in unprivileged mode in ring 3, for example, you can only execute code in user pages. You can only read and write data in user pages. But once you're in a higher privilege level in ring 0, you can access kernel pages. So page tables have this bit indicating whether it's a user page or kernel page, and this is sufficient to provide protection, protection of the kernel from malicious user processes. And modern operating systems do not employ segments. We've seen in a previous lecture that most segments are flat. That is, the base is 0, the limit is the maximum value. All these are flat segments. You don't use segmentations for protection. That is, you no longer check the limit of a segment to see if you are accessing code that you should not be accessing. That is, the limit check is never done for segments. We usually use flat segments. And this one bit distinguishing user and kernel pages is enough. But once you come to virtualization, the model we've seen, you have 3 different entities. You have the guest user space, you have the guest OS, you have the VMM. So this one bit is no longer enough, and therefore segmentation is also roped in for the purpose of protection. So what happens? Segmentation is used to protect the VMM from the guest OS. You still have these user pages and the kernel pages, but within the kernel pages also you have to protect the VMM from the guest. Guest cannot access VMM as and when it wants. So what do? For in ring 3, for user space processes, as well as when the guest OS is running, you will exclude the VMM's memory from the segment. So the code segment, data segment in ring 3 are truncated. These are called truncated segments. They go from 0 to whatever, max minus 4 MB. The last 4 MB that is occupied by the VMM is not allowed for use. either for user processes or for guest process. So when the guest is running in ring 1, its segments, most of its segments like data segment are also truncated to exclude the top 4 MB of the VMM. So therefore, if the guest user process tries to access some address here, this limit check comes up, right? The limit of the segment is only till here, and a violation, a memory access violation will happen. So in this way, ring 3, ring 1, all the segments are truncated except for the code segment. Now when the guest is running in ring 1, recall that the code is in the translation cache. So if you disallow access to this memory, how will the guest OS code run? The guest OS code has to necessarily run in these addresses. Therefore, the code segment in ring 1 points here, but all the other segments, they have no business accessing the VMM. All the other segments are truncated to exclude the VMM. Okay, so in ring 3, nobody needs to access the VMM. Therefore, all segments are truncated. But in ring 1, only the code segment needs to access the VMM because the translation cache is present. And all the other segments are truncated to exclude the VMM part of the memory. And of course, in ring 0, whenever the VMM is running, of course, here all segments point to the VMM top 4 MB code, right? So the VMM only is allowed access to this code. Only ring 0 is allowed access to this code. So in this way, segmentation is used. Note that you couldn't have used just one bit to protect all these entities from each other, right? You have a very complex set of requirements here, and therefore segmentation is roped in to provide all of these isolation and protection guarantees. So of course, there is a special case of a GS segment. So this part of the lecture is optional. Feel free to skip it if you don't follow it. So sometimes what happens is the translated guest OS code also needs to access VMM data, some data structures in the VMM. Like you might have saved some register values, some program counters, and so on, right? So the translated code might need some extra information. For such things, you will write that into the GS segment. Now, in ring 1, normally all segments are truncated. They cannot access VMM data. But the special GS segment is given access to the 4 MB VMM area. So that when the guest OS needs to access some VMM data structures, it can put them in the GS segment. It can give the virtual address as GS colon the address, and this GS segment is allowed access into the VMM area, and therefore certain specific data structures inside the VMM, if the translated guest code needs to access, it will be given access. And of course, if the original guest code, so this GS segment is rarely used in the original guest code. So if regular code wants access to GS segment, that part is rewritten to use some other segment. Anyway, segments are not widely used, so this is not much of a problem. The special use of GS segment will not pose any problems. So finally, this is the summary of an example of a hypervisor VMware workstation built with the principle of full virtualization. This is the reference to the original paper that proposed this idea. This is a very long paper, but some parts of it are easily understandable, and the material in this lecture is taken from here. This is also another reference that compares hardware and software virtualization techniques. So the summary of full virtualization that we've seen today is as follows. This is a way in which unmodified operating systems, without modifying OS source code, you can run on x86 hardware that does not have virtualization support and yet can virtualize unmodified operating systems using the idea of dynamic binary translation. So a summary of what we've studied, we've seen how the VMM design in this paper that we've seen today has a user part, a kernel driver, and both these together trigger a world switch into the VMM context. In the VMM context, the VMM code is running in the top 4 MB, and the guest OS code is translated to run in ring 1 and to trap to the VMM for any privileged operation. So the guest OS code in ring 1 traps to the VMM in ring 0 using the trap and emulate method. And this VMM stub that is running in the guest context can exit back, can perform a world switch back into the host OS context if needed and come back to this kernel driver and user process. And of course, there is a special cross page that manages this world switch where the code and data of this world switch is stored. And this special page is accessible in both contexts, both from the host OS as well as the VMM that is part of the guest context. Both of them access this special page. This allows the storing and restoring of context in both modes. And we've seen how segmentation is used to protect the VMM from the guest OS. And we've also seen how the guest OS traps to the VMM in ring 0 and exits are handled in the host OS. So this is an example of a trap and emulate design-based hypervisor that is built without any hardware support. All the switches between the host mode, guest mode, everything is managed via software without any hardware support. And at this point, it is good for you all to have a good mental model of how this model compares with the hardware assisted virtualization that we've seen in the previous lecture in KVM QEMU. And you should be clear about the similarities as well as the differences that arise from doing the same model without hardware support in this lecture.